Now that we've covered the basics of constructing a triangle and talking about trigonometric substitution, let's talk about the templates. So realistically, when you're dealing with trigonometric substitution, there are going to be three major forms that you look out for. The first one is you have some sort of number squared minus x squared. Right, so that could be like if you had like 9 minus x squared. That's technically 3 squared minus x squared. Or if you had like 16 minus x squared, that's 4 squared minus x squared. But you might also have like 21 minus x squared. So in that case, your a has to be like the square root of 21, which is kind of ugly, but it's just par for the course. And remember, we have the case that that number has to be greater than 0. If it's less than 0, it's a little bit odd, but usually that won't happen with what we're dealing with here. In the case where it's 0 also doesn't make any sense. But if you have something like a squared minus x squared, then the associated triangle is this. We write the square root on the bottom leg, you have x here, and you have a there. So if we use that triangle to construct the substitutions, we'll have that x is a sine theta. Of course, that gives us that dx is a cosine theta d theta. We also have that square root piece is a cosine theta. So again, you can use the triangle to get that, because cosine of theta is this divided by a, and so we multiply over, right? It's this divided by a is equal to cosine. So if I multiply both sides by a, I get it on the other side. So that's kind of the way to do that. Another thing you want to watch out for is this is restricted. So if we're doing like a definite integral and we're trying to integrate with respect to those thetas, theta has to be between negative pi over 2 and pi over 2 inclusive. So you can actually have the endpoints there, but that's just something to watch out for definite integrals. The next piece is if instead of a minus here you have a plus. And that you might think to yourself, well, why does that have to change anything? Well, it changes things because if you tried to put it here, you really have no good way to deal with subtraction. Here, when you square, the square here cancels with that. Well, this doesn't have anything to cancel, so we actually make it the hypotenuse. But that leaves a and x on the bottom and right legs respectively. So then if I take a look at this, the tangent of theta is x over a. So if I multiply both sides by a, I get that x is equal to a tangent theta, which is kind of nice. And then that square root piece, anywhere you see that, it'll become a secant theta. Now, in this particular case, your theta has to be restricted. It cannot include the endpoints. And the reason for that really is that tangent of theta is not defined at pi over 2 because it's sine over cosine. Cosine of pi over 2 is 0, so it doesn't work. So anyway, that's the form here. And finally, this form is the case, instead of being a squared minus x squared, you have x squared minus a squared. Now you have to be a little careful with this one because it kind of splits into two parts. But anyway, so we do the same idea, but instead of it being the bottom leg, we make it the right leg. Now technically you could do this with the bottom leg, it wouldn't be a problem. You could flip these, but it would change what those substitutions are. So the convention that you'll often see is that it'll be on the right leg here. And so if you do the same thing here, you'll get that x is a secant theta, and that comes because cosine of theta is a over x. So secant theta is x over a. Now this substitution is a little funky, right? I end up with a tangent theta or negative a tangent theta. So and this really comes into play when we're dealing with definite integrals again. So if you're dealing in the case where x is less than negative a, so you have, in the case where you have x squared minus a squared, there's this intermediate piece. If you think of the number line, if x gets smaller than a, or the absolute value of a, it can't exist because then you'd have a negative inside of that square root, and we're not dealing with that kind of stuff. So what you actually have is it's on the outside of the number lines. It's at negative or at positive a and I'm thinking in terms of your perspective, positive a and negative a, and they can push out and get larger because when you square it, it's okay. So you have this case. In the case where you're dealing with those negative values, you use this negative a tangent theta, because you actually end up with like a negative here, and that so when you make your substitutions, you actually have a negative. You have a negative going on, or actually, you have a negative going on here. But in the case of a positive case, it's fine. It's perfectly fine here. You also have restrictions on what theta can be, because once you pass over a certain point, well, if you passed in the first quadrant, tangent's going to be positive. In the second quadrant, tangent's going to be negative, so you're actually in that particular case. So again, this is really kind of some definite integral stuff, and that's okay. We can, there are good examples of how to do that, but this is something to watch out for, something you need to be careful about, something to help you keep your wits about you. Now, what we're going to do is we're going to leave these templates up, and we're going to solve a series of problems using them to try to get you comfortable with trigonometric substitution at large.